Thanks to the organizer for inviting me to speak in this wonderful conference. So today I will talk about proof of S-duality conjecture in superstring theory. One point I need to emphasize is that S-duality in general, for those of you familiar with it, is a broad subject. It has many consequences. I'm not proving the S-duality conjecture in totality in a string theory. I'm just proving one of the consequences of it, which is called S-duality modularity conjecture. So let me first just tell you what it means in the point of view of a mathematician, because physicists have written papers on this. I will not mention that, and I just give you a translation of that into mathematics. So S-duality conjecture from mathematical point of view. Okay, so let's start to set up the geometry. Given X, a Calabi-Yau threefold, assume that Picard of X is generated by an ample divisor let's call that divisor L. So then let K be a positive integer, and let H be a smooth element of the linear system K times L. So we are looking at this Calabi-Yau threefold, and we are looking at hypersurface sections inside it, which live inside this fixed linear system of an ample divisor. Now let, say, L denote the generator of H4 integral cohomology of X, which is isomorphic to Z, in fact. And so let's fix some data, I and N. And I'm going to define a certain moduli space of sheaves on this threefold with this data by giving you the churn character of the sheaves I'm considering. So let churn star as a function of these two data, I and N, be given by 0, H squared over 2 minus IL, Euler characteristic of OH minus H times second Todd of X minus N. Okay? So now I'm defining the moduli space. Let, depending on the situation, sometimes I call this churn star of IN, but sometimes I just avoid writing I and N, and sometimes I call it churn star. But it's always a function of I and N, the fixed data.
I is just the second churn class, yeah?
Yes, so yes. I is like, if I give you curve classes, and if I give you, for example, hypersurface section, is the degree of the curve along those.
And what is N? Is it just C3?
Yes. Yes, yeah. So the way you can think about this is that you have this threefold, and you're fixing you're looking at some linear system of divisors on this, and you're looking at sheaves supported on this. Obviously, from the churn character, you can see that the rank of the sheaf on the threefold is 0, but its rank over one of these surfaces is 1. So I'm looking at sheaves which are torsion-free over their support, but with respect to the ambient threefold, they are torsion. So they have some first Chern character, they have some curve class, which is given by this, h squared minus il, and they have some Euler characteristic, which is defined this way. Okay? So now let mh x ch star be denote the moduli space of H semi-stable sheaves in X with Chern character given by Chern star. So for Giesinger stability, you need to fix a polarization, and I'm fixing my polarization to be H, which I defined there. And I'm looking at moduli space of semi-stable sheaves with this Chern character. Okay. Now let's define the invariant. Let dt bar of x with this Chern character, ch star, be the generalized Donaldson-Thomas invariant of x. The reason I call this generalized is because in Donaldson-Thomas theory originally, in Richard Thomas's thesis, he needed this condition that semi-stability of the sheaf, Giesinger semi-stability, is the same as the stability. Generalized Donaldson-Thomas invariants do not need that condition. In fact, these are defined by Joyce. So if you have strictly semi-stable sheaves, you can still define these. So this is due to Joyce and Song. For the purpose of this talk, today I will talk about those DT invariants for which semi-stability is the same as stability. But the reason I'm mentioning this here is because the S-duality modularity conjecture, in fact, is more general than just the stable sheaves. Okay, so remark. When Giesinger semi-stability is the same as the stability, then dt bar is the same as Donaldson-Thomas invariant of sheaves on X with the given Chern character. And since by my assumption X is a Calabi-Yau 3, S-duality tells you that the expected dimension of the moduli space is equal to 0. And so these Donaldson-Thomas invariants are basically degree of the virtual fundamental cycle of the moduli space. So this is what it is. Okay. Notationally, maybe sometimes I write this as dt of x ch star semicolon 1. It means that I want to say I'm integrating 1. Later on, we may discuss situations where x is not a Calabi-Yau threefold, and the expected dimension of the moduli space is some number, and I need to match the degree of the virtual cycle with that cohomology sitting in that degree. So I may put alpha here, meaning that I'm integrating alpha. For now, it's just degree of the cycle. Okay, so given this data, I'm defining my sheaves. Now let's define the generating function of these. Now define the generating function. Let's call this one dt h and I of x, which is I'm adding over all n of these generalized dt invariants, and I'm indexing that by a formal variable q. Okay. Okay. Now let's add over I. So now define, let dt of x is given by summing over all I from 0 to k L cubed minus 1. I cannot be is the degree of your curves against those hypersurface sections, and it's just a finite number. So I'm adding over all of those dti's, but I'm also shifting the series a little bit. So I'm shifting them a little bit by q to the sum ai dt h I of x, and I introduce a new variable q prime to the I. Okay? So this is basically somehow telling you that the generating series of Donaldson-Thomas invariants I'm looking at is somehow understands summing over all curve classes and all of the Euler characteristics. But the way I sum over the curve classes is that I look at all of the curves whose degree against the surface is I. Okay, which this gives you a finite number. So in fact, like for example, if your threefold is quintic, and if I'm looking at hyperplane sections, basically k being 1, this I is some number from 0 to 4. So you can think of this as 5 components, q prime to the 0 times this, sum, plus q prime to the 1 times the sum, q prime to the 2 times the sum. It looks like a vector with 5 components. Now the statement of S-duality. S-duality conjecture. dt of x is a holomorphic modular vector valued modular form of weight minus 3/2 in variable q. Okay? So the reason, again, it's vector valued is because this is finite. You should really think of this as 5 sums, and each one is a modular form of weight minus 3/2 in the variable q. So I'm sure everyone in this audience is already an expert in this, but if you haven't seen this kind of a statement, the story is that, I mean, for us algebraic geometers, q is just a formal variable, but physicists have good reasons to think that this q could be something like e to the 2 pi I tau, tau being an element of the upper complex half plane. So now your sum not only is just a sum, you know, a partition function of your invariance in this formal variable, it could also be thought of as a function from upper complex half plane to C5, to this vector space. So now you have the action of SL2Z on this, and you can ask whether this function, vector valued function, transforms as a modular form. So that's the whole story.
Could you remind me what the exponents AI are?
Sorry, yeah, AIs. So AIs are, I forgot, thank you. So 2I plus h cubed over h, 8 times h cubed minus this. It's just a, which is, well, I don't know. I mean, it's just to, this shift is due to matching this thing exactly with the statement of the physicists. So.
So the first numerator is
2i plus h cubed squared. Okay, so that's that.
Is it something like the dimension of the linear system of this fixed surface?
Dimension of what?
Of the linear system of curves of this degree on a fixed h?
Which one? This? Oh.
I mean, this is some number, but what is the meaning of this number?
I don't know. Yeah, I don't think it's that. Maybe it is. I don't know. I didn't think about it that way. Okay. So.
So exactly which physics paper should we look at to find it?
So I mean several. Let me, okay. So physicists in physics, Gaiotto, Strominger, and Yin studied this for when X is the quintic Calabi-Yau threefold and K is equal to 1. So you're looking at hyperplane sections and over quintic Calabi-Yau threefold. The statement is more general than that. You can have general complete intersections, but in this paper, for example. Then Gaiotto and Yin also, they looked at this separately to study something they call modified elliptic genus. Okay. One thing is that if you look at those papers, since you asked, you will see this generating series, something like they call Z of D4, D2, D0 branes. You know, this is physicists work over real dimensions. So this is their complex surface, and this is a curve on it, some one-dimensional subscheme, bunch of points on it. They call this D4, D2, D0 BPS configurations. And they are writing a sum such as the following. So it is some function z, let's say, of some variable tau times some theta function is a function of tau bar. So, and their statement is that this is a modular form of weight minus 3/2 in the holomorphic variable and weight 1/2 in the anti-holomorphic variable. The thing is that algebraic geometry kind of is blind to the anti-holomorphic part of physics. So we are just proving the holomorphic part of their generating series. So this part. Okay. It's very similar to the story last night where you have this topological string amplitude. It's a function of, you know, some C-infinity section of some line bundle on the moduli of complex structures, let's say of the mirror. It has holomorphic and anti-holomorphic dependence, but we don't see it in Gromov-Witten theory. In Gromov-Witten theory, we just see the holomorphic limit of that physics function. What? No, it's coming. Yeah. Okay. All right. So what do we have so far? Let me just tell you some of the results we already have, some current results. So this was together with Gholampour, who is here, and myself and Richard Thomas in 2014, when the sheaves that I gave you, let's say, are given by ideal sheaves of some curve on this surface, ideal sheaf of a curve scheme theoretically supported over surface over H, moving in this linear system. I mean, these are one honest example of sheaves which are torsion free rank 1 over their support. Their push forward to the ambient threefold is torsion sheaf. Then in this situation, we actually related, we used deformation theory. Deformation theory to relate partition contribution of MNOP invariants. MNOP invariants. These are certain Donaldson-Thomas invariants of ideal sheaves of curves. MNOP invariants of ideal sheaf of these curves in the ambient threefold to our generating series, to the DT X defined above. Okay? So the idea is that if I give you a curve, scheme theoretically supported over one of these elements of the linear system, it has an ideal sheaf as an OH module, but the curve also can be realized as some curve in the ambient threefold, so that has an ideal sheaf as an OX module. And so there is a relation between these two. And the ideal sheaf of that curve over X has a certain DT theory. It's called MNOP theory. And we related contribution of such invariants to our torsion DT generating series. So the reason this is important is because if you actually prove a modularity statement for such sheaves, you can use the relations and state certain modularity consequences for the MNOP invariants. But remember that these are particular type of sheaves I'm considering. The sheaves over there are kind of general torsion-free rank 1 sheaves, but these are just the ones that inject inside the structure sheaf of the surface. So not every torsion-free rank 1 sheaf injects inside O of H. So that's the first result. Then second one, more importantly, together with Gholampour, in 2014, we proved the following statement. When X over C is a K3 fibration, C being the smooth and projective, this could be K3 fibration, could be a smooth or nodal, doesn't matter. I mean, nodal meaning having mild singularities, like rational double point singularities. Then we stated this modularity statement, in fact. So for Chern star, given by 0, some R times this class N, where no? Yeah. Hmm? Oh, yeah. Yeah, that's right, that's right. Yeah, I'm sorry, yeah, that's true. If this is the class of the fiber, class of fiber of pi, then we proved the statement of S-duality. So we showed that dt of this fibration, these dt invariants are given by the following formula. So n is changing from again over z. I'm fixing the i's. And here I will get Euler characteristic of Hilbert scheme of some n minus r times n minus r square of K3 fiber times Noether-Lefschetz numbers of the fibration. These are Noether-Lefschetz numbers. Numbers of the fibration minus some other term. I mean, the fact is that if I fix the curve class inside my surface, if I push forward the homology injects, but the cohomology surjects. So it is possible that I push forward to the ambient threefold and I get a 0 class. So for non-zero curve classes, I will get a term like this, and then I will get some extra term like the following. So Euler characteristic of Hilbert scheme of 1 minus Rn, R squared of K3. So this is the formula for each one of those generating series when n is running over integers. And then you can do the same thing, and you can run over I by summing over all such i's. And so let me tell you what we get. The Noether-Lefschetz, so if I give you the K3 fibration, then, okay, so for each K3, you have the modular space of Hodge structures and so on, you have the Noether-Lefschetz. Then over the fibration, let's say pi, you have the pi relative modular space of Hodge structures, and you have the Noether-Lefschetz locus there. But then there is a section map from this curve C So this is the moduli space of hydrostructures. This is the Noether-Lefschetz divisor there. And then there is a map from curve C to here. Basically, take every point of the curve, send it to the H0 of K of the K3, which lies on that point. And then over here, you get this section. Look at the image, intersect them, you will get the Noether-Lefschetz number. It basically tells you how many of the fibers in the given vibration have holomorphic curves. And it's not, the picture is bad because this could be non-transverse, but then if it is not, you do excess intersection theories.
What is delta?
Kronecker delta. So,
Delta is your delta.
comma. This is Kronecker delta. Okay.
So the Noether-Lefschetz number is related to choice of polarization in the mode of X. The Noether-Lefschetz number is defined for a projective component of the projective. What is the projective K3?
Yes. You look at the Hodge decomposition. You look at the Hodge decomposition. You look at the complexified the moduli space of.
Depends on the choice of L.
So let's see. So should I add here that canonical of X comes from the base? Is that what you want to say? We are looking at situations where canonical of X is coming from the base. So I don't think.
I don't know. Each fiber seems to suggest it comes with an anchor line bundle. No, it's not that. What's the polarization? It's a fiber.
Yeah. That's right.
What's N? Yeah.
Oh. So here is just one. It's just L is just a fiber. L is just a class of fiber. Yeah. And also here we are using the assumption that, assuming that semi-stability is the same as stability. The sheaves could be higher rank over their support, but still I can choose the Mukai vector of the sheaf over the surface somehow that is stable. Anyways,
We don't have the polarization anywhere, not on the surface and not on the X. Maybe you don't need to see this.
For example, could be Lefschetz pencil of cortex. Yeah. Okay, so now we add over these, and adding over I, we've proved that the generating series dt of x is equal to something like this. I'm not going to write down the descriptions of this thing, but I'm going to say what they are. This is the a vector-valued modular form. This was worked by Borchert. This is Borchert's theta function. which keeps track of Noether-Lefschetz numbers. Vector modular form of weight 21/2. And this one is the discriminant cusp form. Cusp form, it is the Dedekind eta function, so it is something like this, which you can also see. This theorem actually tells you that such DT invariants of sheaves supported on the fibers, they are kind of coming from certain contribution of Noether-Lefschetz numbers and then some certain contribution of Hilbert's points on the K3. And when you add them all together, contribution of Noether-Lefschetz numbers are given by Borcher's function, which is this vector value form, of weight 21/2. And this is coming from contribution of Hilbert's points on the smooth K3. And weight of this is weight, basically this 24/2, so it is weight 12. And 21/2 minus 12 is minus 3/2. So in fact, we proved completely the statement of this S-duality conjecture there, as the weight is correct. Okay, so now, what is today's story? In the remaining part of my talk, I would like to somehow tell you that using this information, we would like to generalize this problem for the original, like the way that was originally stated by the physicists, for example, quintic threefold, general complete intersections, not necessarily situations like where your sheaf is very, kind of rigid, or where your geometry is kind of rigid, like that K3 vibration. Okay, so today's story. This is work in progress with Amin Gholampour. We would like X to be a quintic hypersurface. In fact, it could be more general complete intersection, Calabi-Yau 3. But I'm going to just talk about quintic threefold. And K in my definition, I want it to be 1. So I'm looking at sheaves supported on hyperplane sections of quintic. And I want to look at the generating series of invariants and somehow show you that they have modular property. Okay? So let me I'm going to sketch for you the proof, not necessarily just give you all of it in detail. But hopefully I will show you like a flavor of where this modularity comes from. So. Okay. So a sketch of the proof. So we use degeneration technique. So let X, this is my kind of symbol to show degeneration. I don't have any better symbol to use. Let X X1 to X1 union over S with X2 be a good degeneration. To X1 here is a quartic threefold, quartic hypersurface. And X2 is some blow-up of P3 along some curve C, where C is a complete intersection of a, I'm going to tell you why this is this way, a complete intersection of a quintic and a quartic surface. Okay? The fact is that since X is the quintic, you can always degenerate it into a normal crossing of a quartic and a P3, right? Because the degrees add up to 5. And you can look at the total space of this degenerating family, and you will see that it will not be smooth. Its singularity locus is exactly some curve, which is given as a complete intersection of quintic and a quartic surface. Then you can take the total space and you blow it up along the P3 part as a Weil divisor, and it smoothens the whole family. So you will get some degeneration like this. So here, this is quartic, this is some blow up of P3, and this S here inside P3 is a quartic surface. So it's a quartic, which is a K3 surface. Okay? So I would like to tell you about how this degeneration can be realized in the level of moduli spaces. So given this, you can see that if I start from one of those sheaves as a coherent sheaf in X, such that its Chern character is Chern star, which I defined before, then under this degeneration, we can see that the sheaf degenerates into some F1 on X1 and some F2 on X2, such that Chern of F1, let's call that Chern star 1. It is something like some 0, H1, beta 1, N1, some curve class, and some Euler characteristic. H1 is a hyperplane section of X1. And similarly for F2, Chern of F2, which I'm going to call Chern star 2, is going to be given similarly. Okay? So this is somehow that there are certain conditions that need to be satisfied. The Chern characters, these are basically the way that the Chern star breaks into two pieces. So Chern star 1 plus Chern star 2 is the original Chern character. And then you need to have this gluability condition along this surface. So somehow, if you want the language of sheaves, your sheaf sits in the exact sequence F1 plus F2, and it has a quotient. And here you could put F1 or F2 restricted to this surface. And the exact sequence must remain the same. So here, gluability exactly is given by the fact that it doesn't matter which I put here. So in the level of Chern characters, somehow Chern star 1 restricted to S must match with Chern star 2 restricted to S. Okay, so this is for the degeneration of sheaves. Okay, and so this is.
What do you mean by a good degeneration?
Oh yeah, this is just called good degeneration. Yeah. Yeah, it is in the worked out by the paper of Pantripanti and Malik. Yeah, I'm just using their terminology. You can call it degeneration if you like. So this is what is called good degeneration. So, okay, and now what happens to your moduli space? You start from this moduli space of H stable sheaves on X with this given Chern character, star, Chern star, and it degenerates into two moduli spaces. You can pick for polarization over first phono, the quartic, you can pick H1 and X1 with the Chern character 1, and you can pick MH2, X2 with the Chern character 2. However, I'm going to introduce a new notation. I'm going to put these as relative moduli spaces of sheaves with respect to the surface. So let me first give you a background. Those of you who have seen degenerations of Gromov-Witten invariants and so on, probably worked out by Jun Lee in his papers, you can see that somehow, let's say you're counting stable maps to some variety, say quintic, you can degenerate your variety, then somehow the count of stable maps on the original quintic variety can be written as counting curves on the quartic and curves on the other piece. Here it is some blow-up of P3 such that they kind of satisfy certain transversality condition along the divisor that sits in the middle, basically relative condition. So this is the sheaf theoretic analog of that. So these are moduli spaces of sheaves on x1 and x2 relative to S. And I'm going to give you a definition of it. So definition, given some divisor in X and some sheaf, a coherent sheaf on X, F is said to be relative with respect to this divisor D if two conditions are satisfied. If one, tor1 of over OX modules of F with respect to structure sheaf of this divisor vanishes. And secondly, if F restricted to the divisor is pure, is a pure sheaf. It means it doesn't have any subsheaf whose support has dimensions less than the support of restriction. Okay, so this is what it means, relativity. Somehow, in the Gromov-Witten theoretical story that I told you about, so if you have this X with some divisor on it, and if you're looking at curves inside there, the sheaf theoretic object you would like to study is ideal sheaf of the curves inside this threefold, and the condition of the fact that this is called normality, by the way. When this condition is satisfied, it means that this curve intersects the divisor at some points. It has transverse intersection with the divisor, so it means that somehow the co-support of the curve, the ideal sheaf, meets the divisor transversely. If you have sheaves supported on surfaces, like in our case, their co-support somehow their support would meet the divisor transversely, so you will see intersections are given by curves. If you have ideal sheaves of points, for example, inside the threefold, and you want the same condition to be satisfied, it means somehow that the points themselves need to intersect the divisor transversely. So that means they don't intersect the divisor.
So these modular spaces are compact or not?
Good question. So relativity is an open condition. Open condition in the moduli space. So for example, the easiest way of seeing it is the Hilbert scheme of points situation, which I just described. If you're looking at Hilbert scheme of points on this threefold, such that the points do not lie on that divisor, you will get something open, and you need to compactify it. So the whole story of Jun Lee's, the degeneration technique and so on, all of those constructions are actually to give a way of compactification of this moduli space. For sheaf theoretic objects, Jun Lee did it for ideal sheaves, and certain objects in the drive category, they call them stable pairs. He did that for a particular purpose. And he came up with a compactification of this moduli space. For sheaves like ours, we have a way of doing it also.
I'm sorry, this first condition, isn't just that F does not have D torsion?
Does not have what?
D torsion.
What does that mean?
Just don't have sections supported on D. This is just the formulation of this condition. If you just can put for one by using the standard,
Maybe.
and you just have
That's right. It does.
But you said that it gives some non-trivial condition for ideal sheaves of curves.
So wait a minute. So why is it that, let's see. No, I don't see it. Why? I mean, if I tensor ideal sheaf of the curve with the exact sequence of OD, then what sits in the kernel is this tor1. All I'm saying is that tor1 needs to vanish. Why does it need to vanish?
Because it is a subsheaf of zero rank in this ideal sheaf twisted by magnetism.
You mean the what sits before tor1?
No,
On the left-hand side of tor1?
no, just tor1 itself. Tor1 is a kernel automatic.
Aha, yeah. Okay, yeah. Hmm?
For MNOP, where you say the normality is for the structure.
Uh-huh. Okay. Yeah. Mm-hmm. Okay. But for our sheaves, this is the condition that we require anyway. So. Yeah, now I remember. No, you're right, yes. For ideal sheaves of curves, they actually look at the structure sheaf of the curve. For MNOP moduli space, they look at the structure sheaf. You're right, yeah. And then there it is non-trivial that this tor1 vanishes.
No, but I mean, look at the simplest example of lower dimension. If you have an ideal, maximal ideal of a point, and you take a curve passing through each point, then you get the torsion group. This is really an natural condition then for the ideal sheaves.
Say it again.
So if you take a maximal ideal of a point
Uh-huh.
on the surface, and you restrict it to a curve passing through each point, then you are in trouble if it's not pure sheaf. So it is a non-trivial condition even in this case.
Yeah, so you're saying that we definitely need at least purity. The second condition is non-trivial. Yeah.
But
He's talking about first condition. Yeah. He's talking about first condition.
it follows automatic tendency.
That's right. Yeah. No, his comment is about first one. Okay. Anyways, so you get something like this, and so how do we? What would do we do with these relative moduli spaces? Let me write down now the degeneration formula. So let's say I have this M of H1. Now we know what these sheaves are. I can tensor via tensoring by a structure sheaf of the surface, the divisor in between, R1. I will land inside the moduli space of sheaves on the surface. Let's call this one Chern star of S, which is restriction of either of those Chern characters to S. They glue, so it doesn't matter which one I pick. And similarly, on this side, I can also restrict to the surface. And this moduli space also gets a map from here to moduli space of surface. So normality condition basically tells you that now this map is well defined because the drive restriction is the same as restriction. And purity condition tells you that what you will see here is the moduli space of pure sheaves with one-dimensional support on this K3. And this is the moduli space of Mukai. So this is Mukai's.
What about stability?
Well, oh yeah, so S is, we are picking S generically. So it's Picard's Z. So yes. These hyperplane sections are always irreducible. Okay, so you have these maps, and in fact, you can also further structure about this picture. You can take a sheaf with pure one-dimensional support here, and you can send it to the support. And since these are supported on hyperplane sections, for example, here, and their support over here is just a curve of intersection, their support is the linear system. Their support here is just basically quintic curves in K3. So these are genus 3 curves inside that K3, whose linear system is given by P3. So this is all the structure that there is I'm telling you about. And this is the holomorphic symplectic manifold, 6-dimensional, and this fibration is Lagrangian fibration. Okay? In fact, if you like, you can just replace this moduli space with the compactified relative Jacobian, or relative compactified Jacobian. So compactified Jacobian of curves of genus 3 over their linear system. This is what it is. What else? Maybe it's also worth mentioning that if you calculate virtual dimension of this moduli space, its virtual dimension is 3. You can use Grothendieck-Riemann-Roch. You can calculate virtual dimension of this one. That's also 3. And Mukai's moduli space, this one is a smooth, and its dimension is 6. So starting from the generic fiber, where you have expected dimension 0, over the special fiber, you have expected dimension 3 plus 3 minus 6, if you like. So it is 0. It stays the same. And so that tells you that somehow their virtual cycles are related to each other, which is the following way. So since, how much time do I have, by the way?
7 minutes.
Okay. So I will go just a bit faster here, because I need to actually tell you about where is modularity coming from. So if I have these two moduli spaces, R1 to compactified Jacobian, R2, then I can send, let's call this M2, and let's call this M1. I can send M2 times M1, M1 times M2 to this here, and then I have the diagonal here. I can look at the fiber product over here. And the statement of degeneration formula is that degeneration formula is that the virtual cycle of your moduli space of the original smooth variety, in here quintic, is given by summing over all churn 1 plus churn 2s such that they satisfy this relativity condition, compatibility condition of Giessen pullback of product of these cycles. So M1 virtual times M2 virtual. Okay, so that's what it is. It gives you a way of relating sheaves F to all possible ways that it can break into F1 or F2, subject to the fact that the gluability condition is satisfied. Okay, so this is a level of virtual cycles, and if I integrate it, both sides of this equation, somehow roughly speaking, I will get degeneration formula for the invariants. So this is what you will get. So degeneration formula for DT invariants. So DT invariants of H stable sheaves. Yeah. Hmm? Oh, yeah. Sorry, yeah. Yeah. So in some sense, what I'm trying to say is, this is why I wrote this thing. So in some sense, this is a three-dimensional cycle. I push it forward into here. This is a three-dimensional cycle. I push it forward into here. Inside the middle cohomology of this thing, I intersect them. So that's what it is. So your formula for invariance will be some number, I'm not going to put it here, some constant times summing over all churn 1 plus churn 2s, subject to compatibility, dt invariance of H1 unstable sheaves, X1S. I will fill this gap times dt invariant of H2 stable sheaves relative to S, X2S. And so let me put churn 1 star, some class alpha, churn 2 star, some class alpha again. Okay? Remember that I told you that each one of those moduli spaces that they have expected dimension 3. So if you want to make sense of integration over these moduli spaces, you cannot just take integral of 1. Here is the first place where you need to integrate some higher degree cohomology class. And what is this cohomology class for us? Both of these guys, let's say this one, is defined as basically pullback of class of a point. So it is integration of pullback of class of a point over my moduli space. Okay, so you take for the descendant that you see in your integral, you will get point class in here. You pull it back up, that gives you class of a fiber, that's a three-dimensional cycle, and then you pull it back over this moduli space. And then you do that for that one too. So this is the dt invariant for us. Okay, and now why is this modular? Let me just show you a picture. Okay, so why modular? For every given churn character, star, you have a sum of these guys. When you add over churn characters 2, you get a double sum. So in the level of generating series, you will have dt of original x equal to dt of relative sheaf invariance on x1 times relative sheaf invariance on x2. Okay? So if you want to hope for proving modularity statement, you need to show that each one of these guys is modular. So let me just talk about the quintic threefold. I want to show you that relative invariance of quintic threefold are modular. The point is lying exactly on the way that I defined this integral. I want to show you what does this dt mean geometrically. What does it mean pulling back class of a point and then pulling it back to the moduli space. So let's say I start from P3 and I generically pick a point in there. This P3 is the linear system of our curves. As soon as I pick a point on the K3 surface S, that gives me one of those curves of genus 3. And by construction, since these curves are curves of intersection, you immediately get a pencil of hyperplane sections of quintic. Let's say this is X1. You get a pencil of these guys, hyperplane sections in here, which all pass through this curve. In fact, the base locus of this pencil is your curve of intersection that you get from here. And so if I ask you what is the fiber of Mukai's moduli space over this, Mukai's moduli space is fibered over this by all those sheaves which are supported on this curve. And if I ask you what is the fiber of image of, for example, this map, so this has an image. So this thing has an image. And you can ask what is the fiber of that over here. Those are all sheaves with the churn character that I defined before, which are supported on the members of this pencil. So the modularity lies behind basically contribution of this pencil to our DT theory. So now what you can do is the following. So let x1 tilde be the blow up of x1, your quintic, along C, the base locus of the pencil. Let's call this pencil something. This is some pencil in linear system of hyperplane sections of quintic, pencil P. Okay? So what happens is that after blowing up, every point of this curve C, this curve of intersection, will be replaced by a P1 fiber. So this x1 tilde will become a surface vibration. And since these are K3s, x1 tilde is the K3 vibration. So this one is a K3 vibration. And now you can see that the moduli space of sheaves supported on the members of this pencil becomes equivalent to the moduli space of sheaves supported on the fibers of a K3 vibration. And the generating series of such invariants we showed 2 years ago have modular properties. So dt, by result of 2014, this dt theory of x1 tilde has modular property. Property with weight minus 3/2, in fact. Okay? So since I'm out of time, I should just say that just saying that I can blow up and I get some modular form like that is not enough. Next would be, how do you relate the dt partition function of some blow up of this x over some curve to the relative invariance of the curve, the x with respect to s. And for that, you need to do degeneration again. Somehow, using degeneration technique, you can relate this guy to dt invariance of this guy. And from there, you conclude the modularity of this. For this one, similar story happens. You can also prove the modularity of this one using degenerations. And the whole thing will prove the modularity of the original quintic by degeneration formula. Okay, so I stop here. Thank you.
Do I have any questions?
You said that this approach works for any complete intersection.
We hope so.
So you didn't
Yes,
think
no, we hope so.
Did you think about, say, double covers? There is Clement's method of degeneration, double cover of P3 in 2 planes.
Mm-hmm.
So,
Yeah, I haven't thought about it. We hope so. Yep. Well, that's a good question. Yeah, I should have mentioned. Yeah.
Okay, so in that case, not sure what's happening here, but can you? Well, you can hear me, but the question is whether this is supposed to go on the recording. Anyway, can we thank the speaker again?
Thank you.